Hello, beginning Physics 112. Fortunately, I know many of you, but some of you I haven't met yet. So anyway, let's get started and get you ready for assignment 1. But first of all, a few preliminary issues. So let's review Physics 1. So pause the video for a second, look over this list, and see if you recognize everything on here. Okay, so significant figures, scientific notation, and units, those will remain important. I'll keep reminding you. So I'm not going to review those rules, but if you need help with that, come to see me, go to one of the tutors, talk about it in your study groups. Kinematics is motion, so if you read that, you should say, oh yes, I remember that. That's displacement, velocity, and acceleration. We have all those equations. You should keep your equation sheet from Physics 1. In fact, I should probably post it on our website in case you have lost it. Scalars and vectors, this will be incredibly important this semester. And so how to add vectors, vector components, all that trig. If you've forgotten it, it's going to come up in week 1 and in assignment 1. Newton's 3 laws of motion, I'm not going to review them, but the most used of all the 3 is the second law, F equals ma. Energy and energy conservation, work, kinetic energy, potential energy, remember all that? You're going to have to remember it. Momentum, P equals mv, conservation of momentum, an isolated system, right? In an isolated system, momentum is conserved. We know all that. That will come up a lot this semester as well. And that's our conservation laws, conservation of energy, conservation of momentum. And this one we didn't study actually. That's conservation of angular momentum. And finally, we did gravitation. And we learned about vectors and scalars and fields. And in week 2, we're going to go in a big way into that area. Okay. Okay, here we go. Week 1. Oops. Electrostatics Introduction. So the textbook supports this material. I think it's chapter 5. These are the pages. The pages, there's the textbook pages, and then the textbook is a PDF document. It has slightly different page indications, so I give you both of them. You might look that over if that helps you. Keep in mind also that you have lots of other online resources. So watch this video, and if you find other resources that you think are good, you can share those with me and your fellow students. So first of all, we'll talk about electric charge, its nature and its origin. We'll talk about the properties of electric charge. You need to know these 2 important properties of electric charge. It's quantized and conserved. I'll talk about that. How objects are charged, the term electron affinity and electronegativity, conductors and insulators, polarization, Coulomb's law, and the superposition rule. Those are the things I'm going to cover in this lecture. If you're coming back for a second time, you can jump around. That's the advantage to this. So if there's some area of here that you need to review, you don't have to watch the whole video. But for most of you, I think it's a good idea to watch the whole video from beginning to end at least once. Okay, a little review of chemistry and nuclear physics, understanding the structure of matter. Most of you, I hope all of you actually, this is just a review, but let's talk about it. You know about the periodic table, 92 naturally occurring elements and several man-made elements. And each element has an atom of a different structure. So matter is made of atoms, and atoms combine molecules to make compounds. All this should be familiar to you. And if we go to the periodic table and step through the elements, what we see is the first element is hydrogen. And all the atoms are made of three particles: protons, neutrons, and electrons. The protons and neutrons are in the nucleus, and the electrons are in a cloud or shell or orbitals, different ways of thinking about it, around the outside of the atom. Atoms drawn here are not to scale, so if the nucleus of the atom were this big, the electron would fill a volume that's probably 50 to 100 meters in diameter. In other words, the nucleus is tiny, the electron cloud is huge. An analogy is often our solar system, where most of the matter of the sun is in the sun at the center, and the planets just having a little bit of mass are spread out all over the place. Okay, so that's our review. So one proton is hydrogen, two protons are helium, and then it goes 3, 4, 5, 6 protons would be carbon. So hydrogen normally doesn't have a neutron. Helium in its most common form has 2 neutrons and 2 protons, and so has 2 electrons. And carbon, which has 6 protons and 6 neutrons, so 12 particles in the nucleus, and has 6 electrons. And so these are neutral atoms. If you remove an electron from an atom, it's a charged atom, and it's called an ion. And so the fundamental unit of charge in nature is the electron and the proton. And so that's our fundamental unit of charge. We'll discuss that more later. And this is the basis on which we say charge is quantized. You can't cut an electron in half. You can't cut a proton in half and get 2 half charges. In fact, we won't discuss this too much here, but if you cut a proton, it splits into 3 quarks. So there is some structure beyond the proton. But for our purposes, the fundamental units of charge are the proton and the electron. And entering the realm of nuclear physics, we will briefly discuss that if you put a proton and electron together, they become a neutron. Or in some nuclear reactions, a neutron can split into a proton and electron. Okay, so that's the structure of matter. It's important to know that. That's a good model to have, to be familiar with. What is important for us this week is that the electrons are on the outside of the atom and fill the volume of the atom. And so when an atom gets changed or affected or reacts with other atoms, it gains or loses electrons. And that's how we get charged objects. So an atom is usually neutral, but if we ionize it, if we cause it to lose an electron or gain an electron, it can become charged positively or negatively. So, once again, excluding quarks, the electron is the smallest unit in nature of negative charge. We give it a charge unit of E. That's the charge on the electron. This little e doesn't mean electron. It's a symbol for electronic charge. It's the symbol for that fundamental unit of charge in nature. You will see that in general, in the metric system, in the international system of units, the coulomb is the measure of charge. And so we need a conversion factor between 1.6 times 10 to the minus 19 coulombs is the value of 1 electronic charge. So This, of course, existed before we knew about this, and that's why this unit still is widely used, but we need to be able to convert. So the proton has a charge exactly equal to the electron, and that's the unit of one electronic charge, and it's positive, and so it's positive 1.6 times 10 to the minus 19 coulomb. This is all on your equation sheet. So this idea, this recognition, is the quantization of charge. So when we say charge is quantized, we mean that, let me pause the video. So you're asked to explain in words by writing what quantization of charge means. It means that charge in nature comes in smallest discrete fundamental units. Those are the key words to describe the quantization of charge. And those units are the electron and the proton, and the value of charge that they have in coulombs is 1.6 times 10 to the minus 19 coulombs. That statement that I just made is a description of the quantization of electric charge. The fact that electric charge is conserved, remember conservation of energy, we used to say energy can't be created or destroyed, it just transforms from one form to another, right? Like kinetic energy becomes potential, or you drop a ball and potential energy becomes kinetic. That concept is very important, the conservation concept. And in the case of electric charge, the statement should not be that charge can't be created or destroyed, because in fact it can. So the statement should read, let me write it on, let me pause and write it out. Okay, here's the statement for conservation of electric charge. The total net charge, of a closed system is constant. And so if you say charge can't be created or destroyed, that's generally true, but there is an exception to that. In nuclear reactions, a proton and an electron sometimes combine to form a neutron. So we destroyed two charges and got a neutral charge. Conversely, in some nuclear reactions, a neutron can split into a proton and electron and charge is created. So the stronger and truly correct statement is that in a closed system, the total or net charge of that system will remain constant. That's what we mean by conservation of charge as opposed to quantization of charge. Okay, I'm trying to keep this video from being too long. So I urge you to pause the video now and read through this diagram. There's 3 columns and 3 situations. Just pause the video and read through it. That way, when I talk through it, I can go a little bit faster and you'll know what I'm talking about. So do that. Okay, let's walk through these 3 situations. The first one is we have 2 plastic rods. If we hang one up, this is actually what we would do in lab if we had a real lab. But unfortunately, because of COVID, you won't be able to get to do this in the real lab. So this is important. You take a plastic rod, you hang it up so it's free to move, you bring another plastic rod next to it, there's no response. If you take the 2 plastic rods and rub them on fur, both rods, since you're doing the same thing, will become negative and the hung rod will be repelled by the other rod. So just, it's not here explained, but what's happening is electrons are being transferred. So the rod has more, notice the words, electron affinity or electronegativity than the fur. So the rod tends to pull electrons off the fur making the rods negative and not shown here, the fur becomes positive. Why? Because of conservation of charge. So any charge that goes from the fur to the rod will make the rod one charge more negative and make the fur one charge more positive. If you take glass and rub it on silk, which is another thing we would do, notice, of course, if the glass rods are uncharged, they have no influence. Once we rub them on the silk, both rods become positive, and they do the same thing. So like charges repel. If you take the negative plastic rod and the positive glass rod and you hang them next to each other, they will attract. So opposites attract, likes repel. And here it shows you that the fur, since the electrons transferred from the rod to the fur is positive, and so it will attract that rod. And the wool became negative because the wool, I didn't explain that, the wool is more electronegative than the glass, or the wool, notice the term, has more electron affinity than the glass, and so the wool takes electrons off the glass onto the wool, leaving the glass positive. Okay, so this is an activity that we do in lab, and it's going to be restricted now to seeing it on the screen. But those are all important concepts. And if we then, move this out of the way, go back to our list, we see the terms charging objects. We discussed electron affinity and electronegativity. Okay, now we're ready to talk about conductors and insulators. Before we do that, let me just, I have this one diagram, so let me show you just what we were talking about. Here's a piece of fur, here's a piece of plastic, and we see the electrons going from the fur to the plastic. Actually, it's not a very good diagram, because if there's 4 plus 3 negative charges that have left the fur, what we should see is 7 positive charges left on the fur, meaning positive because it's a lack of electrons. Notice, just a reminder if you haven't noticed, protons don't transfer because they're in the nucleus. It's always the electrons that transfer. So things become positive by losing electrons, things become negative by gaining electrons. Just to add an example that comes from chemistry. Hopefully you've had chemistry. Sodium as a neutral atom tends to lose an electron to chlorine as a neutral atom because of their electronic structure. So if you've studied this in chemistry, sodium has one outer electron that's easily removed, and chlorine has a strong affinity for electrons. And so chlorine, under certain chemical conditions, will pull an electron off of the sodium, leaving the sodium positive and the chlorine negative, and then they bond together by this electrostatic attraction, which in chemistry is called an ionic bond. So this part is pretty straightforward. Conductors are material that conduct electricity, allow electrons, those are the charges that move, to move through them, and insulators are materials that prevent the flow of electrons, which later we'll call current. So the key phrase, you want to remember this phrase, is free electrons. Conductors have free electrons. So if you take a conductor like copper, inside the copper are electrons that are not attached to the individual copper atoms, and they're free to move through the copper. Something like glass, which is an insulator, has no such free electrons. For completion, we could name semiconductors, which have a limited conductivity. They're important in modern electronics. And then there are also superconductors, where the electrons move so freely that there's no resistance to their motion. But for this week, all you need to know is conductors and insulators. Examples of conductors. Of these, silver is the best conductor, copper is next. Aluminum, which is not on here, is also a good conductor. And if we were having lab, you would see we use aluminum a lot as a conductor. Gold, actually, I'm not sure about gold. It may be a better conductor than silver. That I don't know. Steel is not a great conductor. Seawater is not a great conductor, but they are conductors, especially because of the salt, right? Those are ions, charged particles in the water. It makes it a better conductor. Rubber, glass, most forms of oil, diamond, wood, and another common insulator is plastic, which is also not on here. So those are just examples of conductors and insulators that you're familiar with. Okay, imagine what you're looking at is a aluminum sphere that's neutral. So it's aluminum, it has free electrons, it has everything is charges in it, but when it's neutral, it just means the charges are balanced and cancel. So the net charge is 0. And so we have this aluminum sphere sitting here, and we bring in and put next to it, let's say, a negatively charged rod that we rubbed on the plastic on the fur. So what happens? Pause the video and think about if you know what happens. Okay, this is what happens. See if you get it right, what happened correct, and the reasons correct. So this rod, the free electrons in the rod, since they're free to move as far away, they're being repelled by the rod, so the free electrons in the rod move as far away as they can get. They move to the far side of the aluminum sphere. Actually, in lab, we do this with a soda can, which is made out of aluminum. And on its side, we can actually do this, and the electrons go over here, and that leaves the positive, a net positive charge on the front side. So that's exactly what happens if you said, oh, the positive charges move toward the rod because they're attracted, and then that's generally correct, but in fact what happens is the electrons are free to move. Free electrons move to the far side, leaving a net positive charge on the near side. And what does that mean? Well, that means that this side of the can is attracted to the rod, and the far side is repelled. But when we do this in class or in lab, you'll see the can attracts, or the sphere attracts to the rod. And the reason is this side of the can is further away, and so the force of repulsion on the far side is weaker than the force of attraction on the near side. And if we were to change the rod so that it were positively charged, we take the glass rod so it's positively charged, what would the difference be? Pause the video and explain to yourself. Hopefully you got it right. Now the free electrons attract toward the rod, so they come to the near side. The positive charges are left behind, unbalanced positive charges. That's even a better way of saying it, because they're all mixed. Right now we have electrons over here, that leaves positive charges over here. The force of attraction of the near side to the rod is stronger than the force of repulsion of the far side with the rod, and so the net effect is the same. So if we did this in lab, which we usually do, is we take a neutral can, we lay it on the table, soda can, we charge a rod negatively, it attracts it. We charge a rod positively, it also attracts it. This is an example of polarization. Separation, a neutral object remains neutral. Notice this is still neutral, conservation of charge, but the charge is not evenly distributed and the can has an electrical polarity. It has a positive side and a negative side. Okay, 5 different situations, A through E. Consider each of these cases isolated from each other. They're not next to each other, they're far apart. These are all point charges, so they're small little spherical charges. And we have 2 equal positive charges next to each other. 2 equal negative charges next to each other. A positive and a negative, a positive and 4 positives, and a positive and 4 negatives. Let me make one adjustment to this. So imagine in each of the 5 cases we start out with 2 neutral balls hung from strings from some rod or fixture, and then we put the charge on them. So what's going to happen to those 2 if they're both positive, both negative, blah blah blah, all 5 situations on these 2 balls? What's going to happen? Predict that. Go through it. I mean, really go through it. Don't just listen to the video. Try and interact and make your predictions for all 5 situations and then come back. Oops, I should have mentioned draw vector arrows. So in the case of this one, they're going to repel and the force is going to be equal and opposite. And if the 2 balls were hanging, they would separate equally like this. And the angle of separation, how much they pushed apart, would be proportional to how strong that force would be, right? So the angle is going to be proportional to the force strength. Okay, so now repeat this situation for the other 4 cases. And then come back. Okay, I'm going to step through all 4 cases. So we did case 1. Case 2 is going to be the same thing, only these will be negative, right? They're going to repel each other equal and opposite, and they'll swing out to a certain angle depending on the force strength. In this case, the force is going to be attractive, and if they're far enough apart that they don't touch, they'll swing toward each other until they're in equilibrium. Remember, the force that's keeping them from going further is there is a force of gravity. We'll talk about that later. So, surprisingly enough, when you get to D, I won't be surprised if you got this wrong, this, when you quadruple the force of this charge, this force vector should be 4 times longer than this vector. I didn't really draw it to scale, but because there's 4 times as much charge here, the force is going to be 4 times stronger, but it's 4 times stronger in each direction. So this you might have guessed wrong. This is Newton's 3rd law. If the force increases 4 times, then charge A is pushed, the first charge pushes on the second charge, and the second charge pushes on the third charge, and that has to be equal and opposite. We'll see that in a minute. And in the case of this one, the force of attraction is going to be equal and opposite, and that force of attraction is going to be 4 times bigger than this force of attraction because there's 4 times as much charge here. And if we added 4 times here and 4 times here, the force would grow by 16 times. And so when we hang these 2 charges, they push each other apart, but at a much steeper angle than these. And the reason they're at the same level is because the force is equal and opposite. The only thing that would make them not at the same level, this will come up in the assignment, is if the mass of one of these 2 balls is bigger. So if the mass of this were bigger, it would be at a lower angle because of gravity. So the quantitative relationship that describes what we were just talking about is called Coulomb's law. And what Coulomb's law says is that the electric force on any charge will be a constant K times the magnitude of the first charge times the magnitude of the second charge, all divided by the distance between the centers of the charge squared. Okay, so K is a constant. We'll discuss that in a minute. And Q is the charge on each object, and R is the distance between them. So if we wanted to quantify any of these forces, those are the quantities we would need. So let's first discuss the K. Yeah, so K is the proportionality constant. Just like in a similar sense, if you remember at the end of last semester, we had the inverse square law for the force of gravity between two masses, like an Earth and a moon, or an Earth and a satellite. And it has the same form, exactly the same form. It's an inverse square law. It depends on the mass of both objects, and it has a proportionality constant G. So here we have the force depending on the two charges and the distance between them, but the proportionality constant is K. It has this value. It's on your equation sheet. You'll notice the units are such that when you use it in the equation, you end up with units of newtons for force. But what will come up in your reading and later on in the course is that K actually is a combination of two other constants, pi and epsilon naught, where epsilon naught, the Greek letter E, with a little zero after it, epsilon naught is a fundamental constant, electrostatic constant of nature. And so why bother with K? Why not just write 1 over 4 pi epsilon naught? That's what a lot of textbooks do. You'll often see that. But sometimes people don't want to write all that, so they have this convenience constant that we call K. So K is equal to this, which is equal to that. And this is the value of epsilon naught, because later in the course we will use epsilon naught all by itself. Okay, now besides the constant, the force depends on, no surprise, the charge on each object. So as we said in the examples, if you double the charge of one object, this whole thing doubles. If you doubled the charge on both objects, then you would be multiplying by 2 and 2 again. The force would get 4 times bigger. But the distance, as we discussed, is squared. So if two objects are a distance r apart, and then I separate them, I move this so it's twice as far away, that's going to be a 2 squared in the denominator. In other words, the force will be 1/4. And if I moved it twice as close, right, halfway, if I move this here, then the force would be 4 times greater. And if I moved it really close, like 10 times closer, remember you're measuring center to center. If I moved it 10 times closer, the force would be 100 times stronger. So that's the relationship of Coulomb's law, and we can use that to solve problems. In fact, that will be your main problem-solving tool throughout most of assignment 1. Okay, here are 2 separate charge arrangements. The first one is 3 charges in a row or along a line. And the second one, a separate situation, is a triangular arrangement of charges where it's arranged as in a equilateral triangle. So let's do this one first. Now there are 3 questions I could ask. What's the force on this charge? The magnitude and the direction. What's the magnitude and the direction of the force on this charge? And what's the magnitude and direction of the force on this charge? Let's start with Q3. What's the magnitude direction of the force on Q3? So if you think you know how to do that, pause the video and try. If not, you can keep watching. Okay, a few things I forgot to mention. In each case, there'll be two forces. So if we look at this charge, we can see that Q2 is repelling it. And so I write that, the convention for writing that is the force of 2 on 3, F23. Then, on Q3, that's what we're looking at, there's a force of attraction due to Q1. So I draw that. Now, why did I draw that so small? Well, what did I call it, right? First of all, I call it the force of 1 on 3. And I made it smaller. Why? Because I can see that this is 6 units of charge, and the distance is, say, 1. So this should be 6 units long. I'm just considering K1, just to get the magnitude, right? Then when I look at this, I see that this is the same charge 3, but this is 1. So this force is only half of this, but it's twice as far away, so when we do the r squared, it's going to be 1/4, so it's 1/8. So I know right away, just by looking at the numbers, this is 1/8 of that. And now if I wanted to actually calculate that, I would see that this is positive and this is negative, and so they have to be subtracted. So I could go ahead and use Coulomb's law and put all the numbers in and get a number for this and get a number for this and then subtract it from that, and then I would have the answer, and the answer would be along the x-axis or in the I-hat direction. So if you're forgetting about IJK notation, we will need to review that at another time. Okay, so that's how we would get that. Let me just write that out for you to see. Okay, I'm realizing that there's a ton of detail here and that in a separate video I should slowly do out a problem like this. But what I have is I have that this this force is the positive force. How do I know? From the diagram. And this force is the negative force. How do I know? Because it's an attractive force from the diagram. And so it would be the larger force minus the smaller force in the I-hat or along the x-axis. And to get this number, I would just use Coulomb's law. I would put in K, Q2, Q3 over R23 squared and take the absolute value, because that could come out positive or negative depending on the signs of these. And then I would find that and subtract it. And I can do this using numbers, but what I didn't give you was the distance. So in this case I said, okay, let Q1 be a positive Q, and let that positive Q be 2 times 10 to the minus 6 coulombs. That's the unit of charge. And that's 2 microcoulombs. So this is the notation we'll be using. So if Q1 is a positive Q, so Q1, notice how this notation is used. Q1 is the name of the charge, and Q is just that quantity of charge. So when we go to Q2, that has twice as much charge, but negative. So Q2 symbolically has a charge of negative Q2. But you're also told what Q is. So if I multiply a negative 2 times the value of this quantity Q, I get the negative 4Q. And what's not there is the value for D, and if you were going to do this calculation, you would need the value for D. But as you'll see in the assignment, in many cases, we will just solve the problem for symbolically for Q and for D and just leave K as K. in future videos, and in some of the videos actually that are already posted, you'll see how that's done. Yeah, so another thing I should mention is that since this charge has two forces on it, why? Because there's two other charges. The total force is just the sum of the vectors. In other words, the presence of, if we just had Q2 and Q3, you would have this force. When we bring the third charge, Q1, in, that adds another force, but it doesn't change this force. So that fact is what is called the superposition principle. So simply stated, it means that the total force on any charge is the simple vector sum of all the forces. Okay, now before we go on to the final situation, just for practice, draw the vectors. If you were going to find the force on Q1, draw the two vectors and label the forces. Do that. So in this case, notice we're talking about Q1. So 2 is attracting this. So you see, this is a positive, this is a negative, and when you multiply, you're going to get a negative number, but the force has to be positive. Why? Because of the diagram. And so the force of 2 on 1 is a vector in this direction, and it's going to be 1 times 2 divided by, say, a distance of 1. So this is going to have a length of 2, just in random units. And this charge is bigger, but it's not much bigger, it's 3. So this would be 3. The force of 3 on 1 would be K times Q1 times Q3. That would be 3. But it's going to be divided by a distance that's twice as far. So if this vector is 2 units, this vector would be 3/4 of a unit. Don't worry if you don't follow that. But that's what the vector diagram would be. When you got these two numbers using Coulomb's law, you would add them, and the final answer would be positive in the x direction or the positive I hat direction. Okay, let's go on to this diagram, and this is the last thing we'll do. Draw the two vectors of the forces acting on Q2. So we're finding the total force on Q2. It's going to be the sum of two vectors, the force of 1 on 2 and the force of 3 on 2. So draw those vectors and then write out what that would look like in terms of solving the problem. So your vector diagram should look like this. You should have the force on this caused by this charge. I didn't write that out. Let me stop. So yeah, so there are two vectors. There's the force of 3 on 2, and that's a repulsive force, so that has to go that way. And if we consider these distances are all equal, so this is just consider the distance 1. So it's 3 times 2. This should be 6 units long, just relative units. And if we wanted to calculate it, this is the equation that we would use to calculate it. This gives us the magnitude. Obviously, it has two components. We'll get to that. And then there's the force of 1 on 2. So this is an attractive force, because this is negative, this is positive. So this force has to go in this direction. And the distance is the same as that. But this charge is a 1 and a 2 rather than a 3 and a 2. So it has to be 3 times smaller, so it's only 2 units. But then to add these two vectors, F12 and F32, we have to find the ij or the xy components using all that vector mathematics that we learned last semester. And so you would get F32x is in the negative direction, F12x is in the negative direction. We would add those two and they would be in the negative x or I hat direction. And then the y component of this one, we would call it f32y would be positive, and we would have to subtract from that f12y, which would be negative, and then we would have the y component. So you can see the result is going to have a positive y component, because this is bigger than this, but a negative x component, and so those two vectors add, and so you would have an answer of components. Then you need to relearn or repractice how to take the components and reconstruct the vector and find the angle. So there's a lot of mathematics there. I'll do that in a separate video later.